Great, it's recording now. Let's cover section 4.8, L'Hopital's rule. The idea behind L'Hopital's rule can be explained using local linearization. Consider two functions f and g such that the limit of f of x as x approaches a is equal to 0 and the limit of g of x as x approaches a also equal to 0, such that the derivative evaluated of a not equal to 0. So if we apply linearization for each function, notice we can approximate locally the function f in blue by this linear function, right? And the function g in orange by this linear function. Now, if you take the quotient component-wise here, you're gonna get that f of x divided by g of x equal to f of a plus f prime of a times x minus a divided by g of a plus g prime of a times x minus a, right? You get this. Welcome deep. We just started. We are explaining L'Hopital's rule. All right. So now we have this quotient approximately equal to this quotient, right? Now, suppose you take the limit here as x approaches to a, and you take the limit here as x approaches a on both sides. Notice since the function is differentiable, f and g are differentiable, then they are continuous at a. So f of a will be the limit of f of x as x approaches a, and this one will be also the limit of g of x as x approaches a, right? Yeah. For this part, since these are constants, they will come out, but this will get canceled. Right? So from here, taking limits on both sides using linearization, we end up with this nice result. Hello, Goya. Hello. We just started. We are talking about L'Hopital's rule, which is going to be a tool, very, very useful tool for us to take limits whenever the computation of these limits is difficult, tricky, right? I will explain. So the idea was, right, that using linearization, this is approximately equal to this, this is approximately equal to this, taking quotients component-wise, we get this quotient here, we get this quotient here, taking limits, we explain, we get to this, right? Now, notice x minus a cancels, and we end up with this super nice result. Look, the limit as x approaches a of the quotient of these two functions, f of x and g of x, is equal to the limit as x approaches a of the quotient of their respective derivatives, right? So this is what basically L'Hopital's rule says. It says that if you encounter trouble computing the limit of the quotient of two functions, if they are both differentiable, you can trade this quotient of the two functions by the quotient of their respective derivatives. And when you do that, L'Hopital promises you that things will be easier computing the limit in this form. You will see on the example, okay? So this is called L'Hopital's rule. Again, this is the conclusion, right? The limit of the quotient of two functions equal to the limit of the quotient of their respective derivatives. And you may say, Professor, we are using now derivatives to compute limits? True, guys. I always say, right, the hero of calculus is the derivative, because the derivative is everywhere, even serves to compute difficult limits, right? You can see as a tool, okay? All right, so now let me explain to you how this works. It turns out this L'Hopital's rule will help us to deal with mathematicians called indeterminate forms. What are these indeterminate forms? These are the four indeterminate forms that we're going to deal with. First one is this 0 over 0. This cannot be computed, right? 0 over 0, you try to put it in the calculator, it will give you undefined. It's therefore called indeterminate form. L'Hopital's rule will help us with these forms. Infinity divided by infinity, another indeterminate form. Nobody knows what it is, right? It cannot be computed. It's not 1, because 1 would be if the quantities are different than 0 and they are real numbers, but they are not. These are symbols, right? Infinity, infinity here. Another indeterminate form is this, 0 times infinity. You may say, Professor, 0 times any number is 0. True, but this is not a real number. This is a symbol, infinity, right? Infinity. So the rules that you know for real numbers cannot be applied here, right? Turns out this multiplication, 0 times infinity, nobody knows what is equal to. It's called an indeterminate form, but L'Hopital's rule will help us with these two. The last indeterminate form that we're going to deal with is this, infinity minus infinity. You may say, Professor, that's super easy. It's 0. Guys, when you subtract two real numbers, let's say real number 7 minus real number 7, that is 0, right? Or a square root of 3 minus a square root of 3, that's 0. That's for real numbers. But remember, guys, these are not real numbers. These are symbols. These are just a trend, right? That's telling you that a number is very huge here, very huge here. But this difference of infinity minus infinity, nobody knows what it's equal to. Okay, it's called an indeterminate form. But however, L'Hopital's rule is going to help us to figure out what to do if we encounter these 4 forms. Okay, that is the usefulness of this L'Hopital's rule. By the way, L'Hopital's rule, in honor to the French mathematician whose last name was L'Hopital, that is why it's called L'Hopital's rule. Okay, so let's start with the easiest undeterminate form, which is this one that probably you are familiar with, 0 over 0. Very common, right? When you take limits, 0 over 0. Yeah, L'Hopital's rule will help us with all of this indeterminate form, but let's start with this, the easiest to deal with. Examples. Suppose they ask you to compute this limit as x approaches 0 of sine of x over x. All right, so first thing that comes to mind is to do a direct evaluation, right? So let me write here, if we try direct evaluation, we are going to get the following, right? If you put this 0 in here instead of x and this 0 in here, clearly what we're going to get is the following. We're going to get this. Sine of 0 over 0, right? Over 0. Let's write nicely this here, over 0. But sine of 0 is just 0, right? 0 over 0, we got stuck here. We got this form, right? We don't know what to do. This is undefined, right? Cannot be computed. So whenever you encounter this, trying to compute limits, don't panic. Just remember L'Hopital's rule. L'Hopital's rule says, right? If we are dealing with the limit of the quotient of two functions, such as sine and the identity function x, right? If when taking the limits, right, of the top and on the limit of the bottom part, we get independently 0 over 0 here, then L'Hopital says, then trade the quotient of these two functions by the quotient of their respective derivatives. Respective derivative, Professor, how does that work? Well, this way. We're going to take the limit as x approaches 0 of the derivative of this guy. Take derivative. Take derivative. And anybody could tell me what is the derivative of sine of x? Take derivative. What should be this derivative? Cosine, right? Very good. Cosine of x, right? Excellent, excellent. Cosine. cosine of x. So you take the derivative of the numerator, cosine of x. Now, derivative of the identity function x, what's that? Take derivative. Yeah, I see on the chat, just 1, right? Excellent, excellent, Deep. Yes, 1, right? Yes, so we write here 1. Following L'Hopital's rule, right? Trade the quotient of these two functions by the quotient of their respective derivatives. We did that. But then you may say, right, Professor, but what have we gained? Well, we have gained the following. Now, try again the direct substitution. And surprisingly, you will see that now it will work. Now it will work. Because now you will get cosine of 0 on the top and 1 on the bottom, right? Cosine of 0 is just 1. Very good, very good. We are headed there. 1, right? And 1 over 1 is just 1, right? So we were able to compute this limit, right? Even though at the beginning we had trouble doing the direct evaluation, right? Using L'Hopital's rule. Very good, guys. So once you take the derivative, basically you try again, right? You try again. So you have to go from here to here. I just did this. Try direct evaluation again. Try again. Direct evaluation. Direct evaluation again, right? And then you will see that it works. Okay. Direct substitution also called, right? Yeah, very good. Great. That was our first example, guys. Let's go ahead with a second example, and then eventually I will ask you to do something on your own. Example 2. Suppose they ask you to take the limit as x approaches 1 of this function, x squared minus 1 divided by x squared plus 3x minus 4. All right, again, if we attempt direct evaluation, writing something on the chat. If we try direct evaluation, you are gonna get the following, right? The following. Deep. Let's go back here, clarifying, right? There is just one answer. This is the answer, the one, not undefined, right? Undefined is trouble that we encounter trying to figure out this limit, right? This limit, but the limit is 1. In mathematics, at this level at least, answers will be always unique, right? Just one answer, unless you are solving a quadratic equation with 2 possible answers, right? But in computations, since we're dealing with functions, univariable functions, the output should be just 1. So this is the answer, Deep. This is clear now? Not undefined. 1, right? 1. You will see, but it's a very good question, Deep, because in the choices, you will see undefined, 1, 0. You gotta go for 1, right? Yeah, very good, very good. Very good, excellent. Yeah. So whenever something is not clear, guys, let me know. Don't hold things back, okay? Very good. So example 2, right? Suppose they ask you to figure out this limit. If we try direct evaluation, this is what we will get, right? 1 squared minus 1 over 1 squared plus 3 times 1 minus 4. 1 squared is 1 minus 1 is 0. 1 squared 1 plus 3, 4 minus 4, 0. Again, 0 over 0, right? Undefined. It's not a number, right? Don't get discouraged for this. Instead, think of L'Hopital's rule, right? L'Hopital's rule is good for this form, for this undefined form, right? So let's just do this again using L'Hopital's rule. Limit as x approaches 1 of x squared minus 1 over x squared plus 3x plus minus 4 should be equal to the following. The limit as x approaches 1 of derivative of this guy over the derivative of this guy, right? Remember, L'Hopital's rule says if you have trouble computing the limit of a quotient of 2 functions, take the derivative respectfully and try again, right? So we're gonna take the derivative of this guy. What should be the derivative of the numerator then? Take derivative. Anybody?
2x plus 3.
This one 2x plus 3. And on the top, derivative of this guy should be just
X.
2x. Excellent, right? Very good, very good. Yeah, so we took derivatives and then we get something simpler, right? Look simpler. And now the goodness of this, guys, is that once you take derivatives, LHopital promises the following. It will work now, the direct evaluation, you will see. Now try again. Try again. Try again, direct evaluation, right? Direct evaluation or direct substitution, also called evaluation. So try again, put in the one here, the one here. Now this is going to be 2 times 1 over 2 times 1 plus 3. 2 over 2 times 1, 2 plus 3, 5. 2/5, right? 2/5. And this is the answer of that limit, right? This complicated limit using LHopital will see easier, right? Easier. All right, so we're gonna go over one more example here. There are two, but perhaps you should practice before we go over more examples. Let me go back to the worksheets and let me give you a couple of questions and then we'll go back to the more examples. Can you try this one, number 2? Using LHopital's rule, can you figure out this limit? We'll write it here, limit as x approaches 5 of x squared minus 9x plus 20 all over x minus 5, right? Try to do this using LHopital's rule. The hint, remember, if you do direct evaluation, you will see that you will get this annoying 0 over 0, right? So this is basically the green light for you to apply LHopital's rule, right? Take derivative here, take derivative here, and try again. Try again. Someone figured this out already, I think. Let's check. Deep. Very good, very good. Excellent, 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 right? Yeah, taking the derivative. Take derivative, right? Take derivative. The derivative of the top will be 2x minus 9. Derivative of the bottom part, 1. Right, 1. Then LHopital says try again now, try again. And amazingly, guys, now it works, right? 2 times 5 is 10, 10 minus 9 is 1, 1 over 1 is equal to 1. We overcame, or we have overcome, the difficulty, right? The difficulty of getting this undetermined form. Yeah, very good, guys. So this is it. Now you may say, right, and often students say, Professor, but you taught us at the beginning that we can do this using factorization. True, guys. If you can factor, you can do it, right? But sometimes, like in example 3, the factorization is not going to be easy. So LHopital is a stronger method, okay? So do this now. Here, factorization, I think, is really out of the question, right? It would take probably a difficult turn if we attempt factorization there, right? Instead, use LHopitals. Yeah. The hint is that if you try direct evaluation, doesn't work because leads to 0 over 0, right? So we get this form 0 over 0 is called indeterminate form, then this means that we can use L'Hopital's, right? So use L'Hopital's rule here, please. And let us know the answer. Take derivatives, right? Derivatives. Derivative. Good. Let's see. Number 3. Check. Deep. Yeah, deep, figure it out. Let me see. Yeah, try guys. Get the derivatives, right? Yeah, there are a couple of attempts there, but I think they are not clear. But deep, you got it. You got it. It's a cubic function, right? Be careful there. Yeah, very good, very good. Yes, I'll go together. All right, guys. So for number 3, if we take the derivative on of the numerator, that is going to be 3x squared minus 2 multiplying 8, 16, 16x, derivative of 7, 0, right? Don't worry about that. Derivative of the denominator now. Derivative of x is just 1, right? And now we try again, right? We try the substitution again. We put it in there. And this is going to be 3 times 1 squared minus 16 times 1 all over 1. I see. Some students added. Yeah, but in reality, you have to subtract, guys. Look, you have to subtract. This is 1 squared is 1 times 3, 3. 16 times 1, 16. 3 minus 16. Okay? Yeah, be careful there. So this is going to be minus 13 over 1. Final answer, minus 13, right? Minus 13. You follow, guys? Minus 13. So should be this, right? Very good. All right, so as you can see, when you deal with a polynomial on the numerator, a polynomial on the denominator, it's not difficult to apply L'Hopital's rule, right? It takes just one application of L'Hopital's rule often, and quickly takes us to the answer, right? To the answer. But let's see what happens if we have some trigonometric functions combined with polynomial functions in this form. So for that, let me go back to the notes and give you more examples, okay? And then we'll go back there. Let's go over more examples here. Yeah, this one is compareless. Take a look at more examples of L'Hopital's rule. Yeah, very good. Yeah, suppose we have this example number 3. Suppose you want to compute the limit of x squared minus 1 minus, over natural log of x. Solution, if we try direct evaluation, what are we gonna get? We get the following. We get 1 squared minus 1 over natural log of 1, right? Natural log of 1. Very good. Now, what is that? Well, 1 squared is 1. 1 minus 1 is 0. Natural log of 1, what's that? 0, right? 0. If you don't, yeah, very good, guys, right? I'm glad that you're aware of that, because this is the exponent that you put on top of e to get 1, and that's 0, right? Natural, if you forgot, you can compute it. Natural log of 1, 0. Very good. 0 over 0, right? It's the form that I can work, is an indeterminate form that I can work around using L'Hopital's rule, right? Very good. So now using L'Hopital's rule, then I can say, right, that this guy, the limit the limit as x approaches 1 of x squared minus 1 over natural log of x. Since I got 0 over 0, is the same as the limit as x approaches 1 of the quotient of the respective derivatives, right? The derivative of this guy here, the derivative of this guy here. So trade the quotient of the functions by the quotient of the derivative. Derivative of x squared minus 1 is just twice x, right? Twice x. The polynomial function. Now, derivative of natural log of x. Anybody remembers the derivative of ln of x or natural log of x?
1 over x.
1 over x. Excellent, excellent, Goja. 1 over x, right? I'm glad that you have memorized these formulas because they are very useful. Okay, so we get this new function, right? Now, LHopital says try again, right? Try again. If you try again, you will see that now it will work. 2 times 1, if I try again the direct substitution, over 1 over 1. Where is that? 2 times 1 is 1, 1 over 1, 1. So this finally equal to 2, right? You follow, guys? Equal to 2. This is the final answer, right? We were able to overcome that undefined situation, that indeterminate form, right? Very good. Using LHopital's rule. All right, very good, very good. So now it's another example here. But before this other example, this deals with radicals. Yeah, I have another one here. Yeah, let's do this one with radicals, okay, once and for all. For you to see how powerful is this LHopital rule. Suppose you have this quotient of these two functions, one linear function divided by one radical function. Again, if we try direct evaluation, meaning if we plug just this into, we're going to get 4 minus 4 over the square root of 4 minus 2, right? 4 minus 4 is 0. The square root of 4 is 2 minus 2, 0. 0 over 0. Indeterminate form, right? But we have now LHopital's rule. So then we can say that the limit as x approaches 4 of x minus 4 over a square root of x minus 2 will be equal to the limit as x approaches 4, right, of the derivative of this guy, which I'm going to place here, over the derivative of this guy that I'm going to place here, right? Derivative of this guy is just 1, right? Derivative of this other guy is what? Remember the derivative of the square root function. We have a formula for that. Recall derivative with respect to x of the square root of x equal 1 over twice the square root of x in simplified form, right? Remember? So we're going to apply this here. Some comments here. Deep. Excellent, excellent. Gonja too.
Yeah, I tried to write same thing. Sorry, Professor.
Yeah, no, it's good. It's good. It's good, guys, that you have this handy, memorized, because in Calculus 2, you will use it so much in Calculus 3 also. So it's worth it to have this memorized. Otherwise, you can have this written somewhere, right? Available handy. Okay, derivative of this guy is this guy. Derivative of 2, 0. Now try again. Try again the direct evaluation. And LHopital's rule, it promises that this time it will work without any trouble. You will see. I'm going to substitute now x with 4. The square root of 4 is 2. 2 times 2, 4. 1/4. But 1 divided by 1/4, or 1 over 4, is just 1 times what you get when you flip this fraction, right? 1 over 4 flip is 4 over 1. 4 times 1, 4, divided by 1, 4. Final answer, 4. That is the limit of this function as x approaches 4, right? 4. Yeah, very good, guys. Excellent. So now, let's see one more example and I will ask you to do some work there. Yeah, but before this, I think, yeah, probably I should give you this because this will require the application of L'Hopital rule twice, I believe. Yeah. But let's see, yeah, twice, but maybe we should do some other examples first. Then I will tell you what to do when you have to apply L'Hopital's rule twice. Okay. Can we try then? Yeah, let's try some and then I will go over that question, okay? Can you try this one now? Number 6, using L'Hopital's rule. Number 6 and number 7, we're gonna do. Take the limit of x over sine of x as x approaches 0. Notice as a hint that if you attempt direct substitution, you will get 0 over 0, right? So use L'Hopital's rule. Gonja. Excellent, excellent. Yeah, very good. Yeah, also deep, I think, figure this out. Yeah, very good, right? If you get 0 over 0, then simply take the derivative, right? Derivative of this is 1. That's what L'Hopital's rule says, right? Take derivative of this. Derivative of sine is cosine, right? And then try again, try the substitution again. But the good news is that now when you try, this will make sense. It's not gonna be 0 over 0 anymore. Cosine of 0 is 1, right? 1. 1 into 1, just 1. That's it, right? Very good. Can you try number 7? Limit as x approaches 0 of sine of 5x over sine of x. Remember at the beginning of this course, I was giving you these kind of things and it would take a lot of tricks to get them done. Now we have a powerful tool, L'Hopital's rule, right? So it's more sophisticated to compute these difficult limits. Yeah, as a hint, notice that if you try direct substitution, you get 0 over 0, so you have to use L'Hopital's rule. Use L'Hopital's rule, right? Yeah, go ahead, take derivatives, okay? Derivative. Gonja, I think you have to adjust. Remember when you take the derivative using the chain rule, you have to multiply by the derivative of the inside function. It's close, but you have to adjust there. Yeah, Miguel, same. You have to adjust for number 7. Yeah, remember the derivative of the composite function is the derivative of side function times the derivative of the inside function. Yeah, try, guys, try. Let me just rewrite here this. Okay, let's do it together, right? Remember, if you attempt direct evaluation, you get 0 over 0, like in here, right? You can apply L'Hopital's rule. L'Hopital's rule says you trade this quotient of these two functions by the quotient of their respective derivative, right? Derivative of this guy. What would be the derivative of this guy? Notice that the outside function is sine, outside function, but there is an inside function 5x. So this is cosine of 5x, right? Times the derivative of the outside function, of the inside function. derivative of 5x, so 5, right? 5. Yeah, and I think this is what you guys were missing. 5. Now, the derivative of this guy, sine of x, is just cosine of x, right? Now, try the substitution again. And we're going to get cosine of 5 times 0. Now I think makes sense. 0, but don't forget there is a 5 there, right? Times 5. Yeah, and that will leave its mark there. Now, Gonja, very good, very good. Excellent. Now it's correct, right? Very good, very good. Yeah, excellent, excellent, guys. Yeah, cosine of 5 times 0 is cosine of 0, which is just 1, right? This cosine of 0, 1. Cosine of 0 again, 1 here. 1 times 5 is 5. Divided by 1 is just 5. So be careful there, guys. When you are dealing with a composite function, don't forget to take the derivative of the inside function. Very good, 5. Now, let's do this, and then I will show you an example where you will have to apply the L'Hopital's rule twice. Try to do this. This is still the same format, but on the next, I think it's coming up. Try this, guys. Limit as theta approaches 0 of 7 minus 7 cosine of theta over sine of 2 theta. Yeah, notice that if you attempt direct evaluation, which is something that you should always try, because what if it works, right? If it works, you are done. Cosine of 0 is 1, 7 minus 7, 0. Sine of 2 times 0, sine of 0, 0. 0 over 0, right? So then apply L'Hopital's rule. Apply L'Hopital's rule. And what is L'Hopital's rule? Well, it's just about taking the derivative of this and taking the derivative of this, right? And then trying again, right? So do that, please. There you go. Derivative. I see some students posting answers here. Number 8. Deep. Yeah, you made my day. Gonja also. Oh, deep. Yeah, great. Excellent. Excellent. Very good. Okay, guys. So here, basically, if you take the derivative of the numerator, you will have to take the derivative of the constant function 7, that is 0. Then derivative of this part. Look, constant negative 7 comes out. Derivative of cosine is minus sine of theta, right? Great. Derivative of this guy is a composite function, right? Outside function sine, inside function 2 theta. The derivative is going to be derivative of outside function cosine evaluated at the inside function times the derivative of the inside function, which is just 2, right? 2. Then L'Hopital says, try again. Now, try again. Substitute again. This is going to be minus 7 times minus sine of 0 over cosine of 2 times 0 times 2. Sine of 0 is 0. Cosine of 0, 1. 2 here, 0 on the top, 2 into 0, 0. Right? The whole thing collapses to 0. Excellent, excellent, guys. They're very good. All right, now, Professor, you said sometimes we have to apply L'Hopital's more than once. So far, we have applied L'Hopital just one time, right? But there are some challenging exercises. You will encounter them on your homework, perhaps, where the application of L'Hopital is needed, but not once, but twice. For example, this kind of thing, this kind of questions. I'm going to give you an example first, and we will go back to number 4, okay? So if we go back here, down here, back to the example, I think it's on the top. Yeah, there are a couple of examples here. This one, for example. Application of L'Hopital's rule twice. Applying or application of L'Hopital's rule. Rule twice. Twice, Professor, what do you mean? Well, I mean the following. I will show you this example. Suppose they ask you to compute this limit, okay? And clearly, if you attempt direct evaluation, right? If you just plug the zero into, right, in an attempt to get this done quickly, you will see that this is cosine of 0 minus 1 over 0. Cosine of 0 is 1. 1 minus 1, 0. 0 over 0, right? But don't get discouraged. We have a method to overcome this situation, right? It's called L'Hopital's rule. So applying L'Hopital's rule, then you will have to say, using L'Hopital's rule. Well, they will say the limit as x approaches 0 of cosine of 8x minus 1 over x squared should be the same as the limit as x approaches 0. We trade the quotient of the function by the quotient of their respective derivatives, right? The derivatives are going to come here. All right, derivative of this guy is derivative of cosine outside function minus sine, right? Minus sine inside function here times derivative of the inside function, 8, right? 8. Good. Derivative of this guy, derivative of x squared twice x, right? Twice x. Now try again. Direct evaluation. Try your direct evaluation again. If you do that, you're gonna get a surprise here. Look, sine of 8 times 0 times 8 times 0. What is this? Sine of 0 again, 0. 0 times 8, 0. 2 times 0, 0. 0 over 0. Professor, did not work. Whenever this happens, don't panic, guys. Just apply L'Hopital's rule again. L'Hopital's rule again, okay? So using L'Hopital's rule again, we will have the following, right? Take this guy. And one more time, take derivatives again. Eventually it will work. So derivatives, derivative, this is 8, this is minus 8 is a constant, comes outside. Derivative of sine, cosine, right? Cosine of 8x times derivative of the inside function 8, right? 8, this is the derivative here. Derivative of this guy is just 2, right? Try again. Try direct evaluation again. And you will see that now it will work. Look, minus 8 times cosine of 8 times 0 times 8 divided by 2, right? This is cosine of 0. Cosine of 0 is just 1, right? 1. Cosine of 0 now 1. So this will be just equal to minus 8 times 1 times 8 over 2. And this in turn is just equal to negative 64 divided by 2, negative 32. Very good. I can comments on the chat. Negative 32, deep, very good, excellent, right? So whenever you apply L'Hopital's rule once and it doesn't work, there is no reason to panic, because if you apply it again, it will work, right? Eventually it will work. At this level, maximum 2 applications of L'Hopital rule, perhaps, no more, okay? But it will work eventually, okay? Yeah. Negative 32, right? It was a little bit tricky, but it worked. All right. So I want you to be aware of this form, right? Where you have to apply L'Hopital rule twice. In order for me to make sure that you will be aware of that, let me ask you to do this guy. Can you try? This is number 4. And then we will do other forms. Do this. Limit of cosine of 5x. Let me put it within parentheses to help you identify that 5x is the angle, right? Yeah, as x approaches 0. Can you do this? Hint. I'm going to give you a hint here. Hint. Apply L'Hopital's rule twice. One will not be enough, right? Yeah. You will see when you try. Let's see. Deep. Excellent work. Excellent. You got it. Yeah, very good. Yeah, excellent, guys. It's not that difficult. It's just application of L'Hopital rule twice, right? Twice. More students. Gonja, excellent. Good work, guys. You made my day. Okay, let's do it together so we can. Excellent, Miguel. Excellent. Very good. Good work. Very good. So yeah, I see, guys. You have mastered the application of this L'Hopital rule, at least for these forms. All right. So let's see. If we try to get this done via or via direct evaluation, right? This cosine of 5 times 0 cosine of 0, 1 minus 1, 0. We're gonna get here 0 over 0, right? Indeterminate form, but we shouldn't panic because we have a way to overcome this indeterminate form 0 over 0, right? It's called L'Hopital's rule. So applying L'Hopital's rule. Well, L'Hopital rule says, okay, trade this guy for this. Limit as x approaches 0 of derivative of this guy, derivative of the numerator, right? And the derivative of the numerator should be derivative of cosine outside function minus sine, right? Minus sine of inside function 5x times derivative of inside function. Derivative of inside function just 5, right? Derivative of this guy is 0. Derivative of x squared twice x, right? Twice x. Great. Now, if we substitute 0 into this, surprisingly, we're not gonna get something meaningful. Still, the 0 over 0 will be there because this sign of 0 is 0. 0 times 5 is 0. 2 times 0, 0 is still 0 over 0 there, right? But for that, we said, don't worry, apply L'Hopital rule one more time. So one more time, take this guy, take derivatives of numerator and denominator. Derivative of the numerator will be 5 and -1, -5, constant comes outside. Derivative of sine function is cosine of 5x times derivative of the inside function 5, right? 5. All over derivative of this guy, 2. Direct substitution again. This time it will work. 5 times 0 times 5 over 2. This is cosine of 0, right? Cosine of 0 is 1. -5 times 1, -5 times 5, -25. The number 2 stays on the bottom, so this should be the value of the limit of that function, right? The limit of this is equal to this. All right, very good, guys. Excellent. This is it. All right, there are some more forms here. Some of them deal with cosines, tangent. So in order to do that, look at this sine and tangent. Let me give you one more example here. Let's go back to the notes. Let me give you one more example here. There are 2 more. Yeah, one more example. Suppose they ask you to compute the limit of sine of pi times x divided by natural log of x as x approaches 1. All right, if you try direct evaluation, you should get this, right? Sine of pi times 1 on the top and natural log of 1 on the bottom. But this sine of pi, since on the unit circle pi is right here, right? And it has coordinates -1, 0. The second coordinate gives you sine, right? Sine of pi is 0. You can get this in the calculator as well. 0. Natural log of 1, we saw before, is just 0, right? So we got this indeterminate form, 0 over 0. No problem, we have a tool to overcome this situation, right? Using L'Hopital's rule, using L'Hopital rule, we can say that the limit of this guy as x approaches 1 should be equal to the limit as x approaches 1 of the derivative of this guy in the top here, derivative of this guy in the bottom here, right? Derivative of sine of pi times x. What's that? Derivative of sine outside function is cosine, right? Cosine of pi times x times the derivative of the inside function. Derivative of the inside function, just pi, the constant, right? On the denominator, derivative of natural log of x is just 1 over x, right? Then try again. Direct evaluation. After taking the derivatives, right? If you do that, you will get that this is cosine of pi times 1 times pi over 1 over 1, right? Substituting 1 for x. This is cosine of pi times pi divided by 1. What is cosine of pi? Cosine of pi in the unit circle again, since pi is here, right? This guy has coordinates -1, 0. So cosine always the first coordinate, right? So cosine of pi is -1. Believe it or not, guys, -1 times pi divided by 1. -1 times pi is negative pi divided by 1, negative pi, right? So negative pi should be the answer, right, for that question. In case, guys, you have difficulties computing cosine of pi, that can be gotten in any scientific calculator. You go to functions, cosine of pi, There you go. But make sure you are working in radians, -1, right? Not in degrees, in radians, right? -1. It's the limit as x approaches 0 of sine of 4x over tangent of 9x, okay? Yeah. Let me rewrite it here. Limit as x approaches 0 of sine of 4x over tangent of 9x. Remember, if you attempt direct evaluation or direct substitution, you're going to get yourself in trouble because this is what's going to happen, right? Sine of 0, 0. Tangent of 9 times 0, 0. Tangent of 0 is 0. 0 over 0, right? Indeterminate form. But don't panic because we have LHopital now to overcome this situation, right? So using LHopital's rule, then we're going to get the following. The limit of sine of 4x over tangent of 9x is just equal to the limit as x approaches 0 of derivative of sine of 4x is going to be derivative of the outside function sine is cosine of 4x times the derivative of the inside function 4x, 4, right? 4. At the bottom, derivative of tangent. What is that? Derivative of tangent is secant square, right? Secant square of 9x times derivative of 9x, derivative of the inside function 9. Now, LHopital says try again. If we try the direct evaluation again, now substituting x for 0, we get cosine of 4 times 0, all multiplied by 4. Then secant square of 9 times 0 times 9. This is just 0, right? 0. This is just cosine of 0 times 4. The 4 is outside. And this is secant square of 0 times 9. Cosine of 0 degrees is, or 0 radians, if better said, 1, right? Now, what is the secant of 0? Remember, cosine of 0 is 1. So then 1 over cosine of 0 has to be also 1 because 1 over 1 is 1. But this is secant of 0, right? So secant of 0 is 1. 1 is square, 1. So this will be 1. 1 times 9, 9. 1 times 4, 4. Excellent. This is it, right? 4 over 9. This guy. Excellent. Okay, guys, enough with this form, in this indeterminate form 0 over 0, right? Let's explore other forms. The rest of this you can do it at home. If we have time, we can go back to some of these forms. But now let me talk about the other indeterminate form, infinity over infinity. This. Right, the second one, right? Yeah, so how to apply or to use LHopital's rule when you get infinity over infinity? Well, let me explain to you that with this example. Suppose they ask you to evaluate this limit as x approaches infinity of x squared plus 3x minus 10 over 7x squared minus 5x plus 4. What to do? Well, first, if you attempt to just plug into infinity, right? Thinking of plugging into a huge number like 1 million, 1 billion, right? Just plug it into to see what happens, right? Then you will get the following. Remember, this guy, infinity is a huge number, right? When a square, even bigger, right? So infinity, right? Infinity square, infinity. 3 times infinity, infinity, right? And infinity minus 10, comparing infinity with 10, 10 is nothing. So this ends up being just infinity, right? Infinity at the top. On the bottom, again, infinity square, huge number, infinity times 7 is still infinity. Here, minus this 5 times infinity. this infinity square compared to this swallows up this one, and then in the end you get infinity as well, right? Great. So infinity over infinity. But L'Hopital will help us with this form as well. So using L'Hopital's rule, we can say that this will be equal to L'Hopital's rule. This will be equal to the limit as x approaches infinity of the following. We're going to trade these functions by their respective derivatives, okay? So using L'Hopital's rule, this will become derivative of this guy. Derivative of this guy. Well, great, 2x plus 3, right? Excellent. And this one, the derivative of this guy?
14x plus minus 5.
Derivative, excellent. 14x minus 5, right? Looks better now, right? But now it plug into infinity. 2 times infinity plus 3, 14 times infinity minus 5. This is 2 times infinity, infinity, plus 3. 3 is nothing for infinity. Infinity swallows up 3, infinity. Here, 14 times infinity, infinity, minus 5. 5 is nothing, relatively speaking, compared to infinity. So infinity, infinity over infinity again, Professor. Yeah, but remember, if it doesn't work when you apply L'Hopital's rule once, apply L'Hopital's rule again, right? So if you apply L'Hopital's rule again, you will see that taking derivative again, derivative of 2x plus 3, what's that? Well, 2, right? Excellent, 2, just 2 here. Derivative of 14x minus 5.
14.
Very good, derivative, right? Take derivative again, apply L'Hopital's rule again. I got this, now no trouble, right? So the limit is just 2 over 14. Be nice and simplify, right? Mathematicians will appreciate it. 1 over 7, right? Yeah, because they always post the answers in simplified form, right? So 1 over 7 will be the limit of this function, right? Applying L'Hopital's rule if you want to, right? There are other techniques that, remember, I showed you another technique, dividing by the highest power of the denominator. Also, that can be applied, but turns out sometimes, in some cases, only L'Hopital's will help. So let's try to learn how to apply this, right? For example, here, look, this is no longer a polynomial, right? The other method applies to polynomials, but what if they give you something like this? Let me show you this, number 8 now. For number 8, again, if you just apply a direct evaluation, right? Direct evaluation will lead you to the following. If you just plug infinity here, you will get on the top natural log of infinity, on the bottom 5 times infinity. But what is natural log of a huge number? Well, for that, recall that if you look at the graph of the function natural log of x, it looks like this, right? This is f of x equal ln of x. This point is known, is 1,0, right? But what if you take a huge value here, infinity? Where this will, what this will be? Well, this keeps growing, right? Growing slowly, but growing. So this infinity will end up being yes, infinity, right? Limit of natural log of infinity, infinity, because again, it grows. Some comments on the chat. It keeps growing, right? Without bound, slowly, but keeps growing. So infinity, right? Infinity there. All right, it's infinity. 5 times infinity, infinity. Again, infinity over infinity, right? Yeah, but we have, what you guys trying to figure it out. Very good. So now apply L'Hopital's, right? Using L'Hopital's rule. Then you say, okay, limit of natural log of x over 5x as x approaches infinity equal to the limit as x approaches infinity of the quotient of the respective derivative. Gonja said derivative of natural log of x, 1 over x, right? Derivative. Derivative of 5x is 5, right? And then LHopital says try again. Try again. Direct evaluation. If you try again direct evaluation, you will see now that this will be 1 over infinity over 5, right? But what is 1 over infinity? Imagine instead of infinity, you have 1 billion. 1 billion into 1 is going to be 0.00 dot, 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 0, 0, 0, 0. In the limit, this goes to 0, right? So it's 0 over 5. Final answer, look, 5 into 0, 5, 0, sorry, 0. This is the final answer, right? You see, guys? Yeah, so it helps us also to evaluate this type of indeterminate forms, right? Before we go over the next indeterminate form, let's practice in this part. Let's practice here. Go to the worksheet. So if you encounter infinity over infinity, just apply LHopital's rule. Sort of in the same way you apply LHopital's rule for 0 over 0, right? Yeah, let's choose something nice and reasonable here. Let's see. Can you try the first one? Yeah, this one's. Yeah, warning, you may have to apply LHopital's twice. I can do this. X squared plus 4x plus 7 over x cubed plus 4x squared plus 10. Notice that if you apply just direct evaluation, you're going to end up with infinity over infinity, right? So therefore, we have to apply LHopital's rule. Infinity over infinity. So apply LHopital's rule then. Yeah, hint, use LHopital's rule twice. Once will not be enough. Let's see. Gonja, yeah, you made my day. Excellent, excellent. Very good, very good. Excellent, excellent. Yeah, very good, very good. Yeah, very good, very good. So let's just apply our LHopital's rule, right? LHopital's rule says take derivative of numerator and denominator. Derivative of the numerator will be twice x plus 4 here. X approaching infinity. Derivative of the denominator will be 3x squared plus 8x. Derivative of this guy 0. But turns out if you substitute at that point, it might not be enough because look at this. Look at what happened here. 3 times infinity squared plus 8 times infinity. Again, this is infinity plus 4 infinity. Infinity squared infinity times 3 infinity plus 8 times infinity infinity. Again, I got stuck with this indeterminate form. So again, apply LHopital's rule. Derivative of the numerator is 2. Derivative of the denominator 6x plus 8. Substitute infinity again, but this time the good news is that it will work. You will see. This is just 2 over 6 times infinity infinity plus 8 infinity. Infinity into 2, a huge number into 2 in the limit is 0, right? So this one 0. Yeah, very good, very good. So this one, excellent. Yeah, And then we know this in advance, right? When we study limits at infinity, right? It is an alternative, right? It's a very, very algorithmic, quick. The other method is to detect or to realize that this is boron heavy, and boron heavy end up always with this limit, right? Boron heavy rational functions. But this, the goodness of this method is that it works even if these are not polynomials, right? So this you can do at home. Let's try something new. Let's see, for example, this type of things, right? For that, we have to understand what to do with other forms. But before that, let me just do quickly this one just to make sure that everybody is okay. Let's do number 5 and then we'll move on for the next one, okay? Do this. Limit of 2x plus 9 over 7x squared plus 5x minus 4 as x approaches infinity. As a hint, I can tell you guys that if you try to substitute infinity here, 2 times infinity, infinity plus 9, infinity, infinity squared infinity times 7, infinity, 5 times infinity, infinity, infinity plus infinity, infinity minus 4, infinity, right? So you get this, but then use LHopital's rule. See? Number 5. Very, very good, Gonja. Very good. Very good. Excellent, excellent. Yeah. Very good, very good. So taking derivatives, I think it will be enough the application of the LHopital's rule once for this one, right? We can say that this is going to be the limit as x approaches infinity of derivative of this guy, which is just 2, right? Derivative of this guy, which is just 14x plus 5, right? But now, if you try again, you will see that now this will give us some meaningful number. 2 over 14 times infinity, infinity plus 5, infinity, infinity into 2, 0, right? 0. And that's consistent with the fact that this is boron heavy, right? Boron heavy rational functions, they lead to this limit 0 there. Very good. Okay, so now let's talk about this form, right? This form. For that, I have to explain to you what to do, and then we will deal with these radical, tricky forms. All right, so let's go back to the notes and let me explain to you what to do if they give you something like this. I will show you. This is the third indeterminate form, 0 times infinity. 0 times infinity, right? You may say, Professor, isn't this 0? Yeah, that's for real numbers, right? 0 times any real number, 0, but 0 times a symbol like infinity, nobody knows what this is. Mathematicians call it an indeterminate form. But good news is that LHopital's rule will help us with this indeterminate form. You will see. Suppose they ask you to evaluate this limit. The limit of the function x times natural log of x as x approaches 0 from the right. Solution. Notice, if you just attempt a direct evaluation, this will be 0 times natural log of 0, right? But this is the problem, natural log of 0. This is 0, but what is this? Recall, if you look at the graph of the function f of x equal natural log of x, notice that for input value 0, there is no output value, right? This curve gets closer and closer to the y-axis, never touching it, right? So this is considered to be what? Since it's going down here, right? Somewhere, never touching the y-axis though, right? It's headed or it's approaching negative infinity, right? So this in theory should be negative infinity. 0 times infinity, 0 times infinity. This is called indeterminate form, right? Indeterminate form. Indeterminate form. So we can use LHopital, right? But now it gets tricky here because notice that in order to use LHopital, I need a quotient of two functions, right? I need a division of two functions, right? Here I have the product, the multiplication of two functions, right? So we're gonna follow a trick here, a trick. I see someone wrote something on the chat. Let me read it. Yeah, we need a trick here. Yeah, we will see what this is equal to. I think you may be right. Yeah, so now notice, right? I need a quotient, so I'm gonna apply this trick. I am going to say that this guy, right here better, should be equal to the following, algebraically speaking, right? Limit as x approaches 0 from the right. And it's from the right because approaching 0 from the left doesn't make sense for this function, right? Yeah, so I hope you will be okay if I write this out. Natural log of x over 1 over x. 1 over x. It's a crazy trick, algebraic trick, right? Instead of writing x here, I put it down here as 1 over x. Remember, when you divide these two guys, you flip this x over 1 times natural log and you get this, right? So this and this are algebraically the same. So when you want to go from a product to the division for this form, do this trick, right? Follow this trick. But now notice that if I substitute here, I will get natural log of 0 over 1 over 0, right? This is 0, 1 over 0, not 0, infinity, right? Look, when you are close to 0, negative infinity, and this will be infinity, right? So I'll get the infinity over infinity form, which allows me to apply LHopital's, right? LHopital's rule. So apply LHopital's rule using LHopital's rule. I'm gonna write this 1 over x as x raised to minus 1, because next I'm going to take derivatives, right? Taking derivatives. Derivative of natural log of x is 1 over x, right? Derivative of this x raised to minus 1 is minus 1 coming down, x raised to 1 less stays here as exponent, right? Minus 1, minus 2, right? Minus 2. But now this becomes the following. It's some crazy algebra here, right? But in the end, we will see that we will end up with something meaningful. This is this, right? I just put this down. I'm dividing these two. Limit as x approaches 0 from the right of what? 1 over x times what I get when I flip this, right? And don't forget the negative sign there, right? So this will be x squared over 1. Finally, look, limit of minus x squared over x as x approaches 0 from the right. And finally, limit as x approaches 0 from the right of minus x, right? And this, guys, when you substitute here, makes sense. It's minus 0. Finally, this whole thing equal to 0. Application of LHopital's rule, right? Tricky though, very tricky. All right, so this was one of the forms. We're gonna use this form 0 times infinity together with L'Hopital's rule to overcome this indeterminate form, right? Yeah. So let me ask you to do something on your own similar to this, okay? So when you see a product, guys, just apply this trick, right? And then we will go over the radical form, which is the last form. So let's try this, for instance. Where is the worksheet here? Yeah, I saw it somewhere here. This, for example. Can you try this? Limit of x times sine of 15 over x as x approaches infinity. Notice if you try to evaluate infinity directly here, this is what you will get. Infinity into 15 is 0, sine of 0, 0. You get the this indeterminate form, right? 0 times infinity. Their form. So use L'Hopital's. But in order to use L'Hopital's, we need a quotient, right? So I'm going to give you this extra hint. We have to put this down this way. Over 1 over x, right? Use this. So that, look, this 0, the 0, 0 over 0, so you can apply L'Hopital, right? So now apply L'Hopital. Derivative, derivative. Yeah, go ahead, guys. And try to remember this for your homework because some questions are a little bit difficult there. Let's do it together so we will have time for the last two forms that are difficult. Some students posted answers here. Let's see. Let's check. Number 6. Gonja. Yeah, you made my day. Excellent, excellent. Yeah, it's very tricky. Very good, very good. Excellent, excellent. Yeah, let's do it together, okay? So using L'Hopital's rule, we have to take the derivative of this guy. But the derivative of this guy is what? Cosine of inside function, that I can write it like this, right? And times the derivative of this inside function, which is negative 15 x raised to negative 2, right? Very good. Derivative of this guy, this is x raised to minus 1, right? So we'll minus x raised to minus 2. Now notice, right, that this guy and this guy are the same. I can cancel them, right? Yeah, let's cancel them. This cancels with this. What is left? Minus also cancels with minus, right? Minus or minus plus. 15 is left, right? 15 times this. There, do the substitution. So cosine of 15 over, let me write this down here, over infinity, right? Over x times 15. But this guy, infinity into 15, is just equal to 0, right? Times 15 here. Cosine of 0 is 1. 1 times 15, 15, right? And that's it. Excellent, excellent. This guy, right? Excellent. For number 6, the last one, D. All right, guys, so great. So now let me show you the last form, right? And I'm gonna go over a couple of examples, perhaps because it's very tricky. It involves, in some cases, it requires, better said, a change of variable. I will explain. But first, let me show you this form, okay? The last indeterminate form, right? We dealt with 0 over 0, infinity over infinity, 0 times infinity, and now the last indeterminate form is this, infinity minus infinity. What to do if you encounter this indeterminate form? Well, example, suppose they say evaluate this guy. The limit as x approaches 0 from the right of 1 over x squared minus 1 over tangent of x. How we deal with this? Well, notice that if you just go ahead and try to evaluate directly, right? Putting 0 there, 0 squared here, minus 1 over tangent of 0. Unfortunately, you're gonna get here 1 over 0 minus 1 over 0 is infinity minus infinity, and that is an undeterminate or indeterminate versus form, right? Indeterminate form. But we have L'Hopital's rule, right, to overcome this situation. So using L'Hopital's rule. So using L'Hopital's rule, you're gonna get the following. Well, first, let's work this out, right? Because in order to use L'Hopital's rule, remember, we need the quotient of two functions, right? The division of two functions. This is not showing that. So what I'm gonna do is I'm going to combine these two fractions, right? I'm gonna subtract these two fractions using the LCD of these two guys. LCD of x squared and tangent of x. LCD is just the multiplication, x squared multiplied by tangent of x, right? That's the LCD. What does it mean? It means that this guy must be multiplied by tangent of x, numerator also by tangent of x, and this guy to complete this LCD by x squared times x squared here, right? Top and bottom. Now let's do the sum here. So this will become the limit as x approaches 0 from the right of tangent of x over x squared tangent of x minus 1 times x squared here, x squared over x squared tangent of x, right? It's just algebra here, right? And this becomes the following. Limit as x approaches infinity, not infinity, 0 from the right of this tangent of x minus x squared all over x squared multiplied by tangent of x, right? Follow, guys? Now I have a quotient. And moreover, if I substitute 0 there in that quotient, I have, look here, tangent of 0 minus 0 squared over 0 squared times tangent of 0. Indeed, I get 0 over 0, right? Which allows me to apply L'Hopital's, right? So let's apply L'Hopital's rule. So L'Hopital's rule says take derivatives, right? Taking derivatives of numerator and denominator respectively, we get the following. Limit as x approaches 0 from the right of derivative of this guy, the numerator, is going to be derivative of tangent secant square, right? Derivative of x squared twice x, right? Derivative of this guy in the bottom. Here I have the multiplication of two functions. So call this function f, call this function g, apply your product rule. Product rule says, remember, derivative of f times g is f prime g plus g prime f, right? So derivative of f start with that, twice x times g, tangent of x, plus derivative of g, derivative of tangent is secant square of x times f times x squared. Right? And now substitute 0, and you will see that then this will give us some meaningful number there. Substituting 0, 2 times 0, tangent of 0 here, plus secant square of 0 multiplied by 0. Here, I see that secant of 0 is just 1, right? This 2 times 0 is 0. 2 times 0, 0, tangent of 0, 0. Secant of 0, 1 times 0, 0. I end up with this 1 minus 0 over 0 plus 0, which ends up being 1 over 0, which is just infinity, right? Infinity. Small number into 1, huge number, infinity. So we got for this answer infinity for this limit, okay? All right, guys. So now this is in case, for the case infinity minus infinity, right? How to deal with it. Sometimes you will get a number. I will show you another example. But now I really want you to pay attention to this example I'm going to do now. This is going to help you in your homework. It's number 7, I think. Let me give you one example and then you will do some others, okay? Yeah, number 7, number 8. Yeah, let me do number 7 here, okay? This you have a space here. It's very tricky, this one. Then I will ask you to number 8. For number 7, they are asking you to get the limit as x approaches infinity of the square root of x squared plus 2x minus x, right? And notice that if you just plug this into, you will end up with what? You will end up with the square root of infinity squared plus 2 times infinity minus infinity, right? This is infinity plus infinity, infinity, a square root of infinity, infinity. You end up with this indeterminate form, infinity minus infinity, right? So it means that we can apply LHopital. But now, before applying LHopital, I want you to use a change of variable, because without a change of variable, this will be really difficult. Try to learn this technique, it's going to help in the future. Sometimes, instead of having here a variable approaching to infinity, it is better to have a variable approaching to 0. That is accomplished by using this change of variable. Use change of variable. Let y be 1 over x, not x, 1 over x. If you call 1 over x y, then x has to be equal to 1 over y, right? And not only that, if x approaches infinity, then y should approach what? Y should approach, since look, y is the reciprocal of x. If x is huge, right? Imagine x being a trillion into 1, in the limit, basically this guy will go to 0, right? So if x approaches infinity, then y gets really small, goes to 0. So we have this. Now, then we can say that this guy then, right? This guy then will become the following. Will be limit as x approaches infinity, but as x approaches infinity, y approaches 0. So y approaching 0 of what? The square root of 1 over y squared plus twice 1 over y, right? That's x, we call it, to 1 over xy. So x is 1 over y, right? Minus here 1 over y. Work that out. This will help you because now we have a limit where y approaches 0, right? Yeah, great. Let's do the algebra here. Let's do the algebra there, which is a little bit cumbersome, but you will see that not that bad. Look, 1 squared is 1, y squared, plus 2 times 1, 2 over y, right? Look at this sum. Now, taking the LCD of y squared and y, that is just y, right? LCD y. Square, actually, right? The one with the highest power. So this means that I have to multiply this by y to get the LCD here, right? So simplifying this, I get this as the limit as y approaches 0 of 1 over y squared, 1 plus 2y over y squared, right? This is y squared, common denominator. So let's write it directly there. So we can get this done. 1 plus 2y over y squared minus y squared here. 1 over y squared. So now notice that doing this minus 1 over y, right, will simplify things because now the square root of y squared is just y. This is also y. So I end up with this, right? 2y minus 1 over y. This is limit as y approaches 0. Now, if you substitute 0 there, you will get 1 plus 0 minus 1 over 0. This is 0 over 0, right? So I can apply L'Hopital, take derivatives. Derivative of this guy will be 1/2, 1 plus 2y raised to minus 1/2. And the derivative of this guy is 1, right? At this point, just substitute 0 in there, and that will be it. That will be it. 1 plus 2 times 0. Yeah, and this is really the worst this could get. 0 disappears. 1 raised to this negative 1/2 is just 1. 1 times 1/2, 1/2 divided by 1, 1/2. So all this madness, guys, to get the 1/2 as our final answer, right? Yeah, but let's see. I think I forgot something here, or everything's okay there. Let me check, double check. Yeah, I think everything is good. Yeah, everything is good. Yeah, but I think I forgot that 2 here. There was a 2. The derivative of the inside function, right? Derivative of this is 2. Yeah, these 2 will cancel these 2. So this will be just 1, right? 1. Yeah, this is, guys, the worst this could get, but using L'Hopital's rule, you can do it, right? Yeah. Let's try to finish up with this one, number 8. Let's see if you can figure this out. Try to do this. But the rest are easy, really. This, I will give you the hint, right? Again, we have this similar form. So since when plugging into, you get infinity here minus infinity, we are supposed to use L'Hopital's rule, but for that, use the change of variable. Let y be 1 over x, okay? Let's use a different color so we can follow this. Yeah, let y be 1 over x, then x is 1 over y, and if x approaches infinity, then y, since this is reciprocal, approaches 0, Use this, right? And redo this. So let me rewrite this here. This guy will become this other guy. Limit as y approaches 0 of then do the change of variable, right? A square root of 1 over y squared, that's what is x, plus 6 times 1 over y minus 1 over y, right? Do the algebra here, and then you apply L'Hopital's rule, and that should take you to the answer, right? Try, guys, try. I'll give you some time. Yeah, let's do it together so I can show you number 12, okay, which is going to be the last one. Okay, doing the algebra here, this will become the limit as y approaches 0 of the following, right? 1 over y squared plus 6 over y. Let's erase this part. Minus 1 over y. Minus 1 over y. But this sum, once you realize that the LCD is y squared, multiplying this by y, multiplying this by y, you're going to get that this is going to be the limit as y approaches 0 of the square root of 1 plus 6y on the top, on the bottom, square root of y squared, but that's just y, minus 1 over y, right? But together, since they have common denominator, this is limit as y approaches 0 of a square root of 1 plus 6y minus 1 over y. Applying L'Hopital's rule, because if you substitute 0 here, you get 0 over 0, right? Using L'Hopital's rule, using L'Hopital's rule, derivative of the numerator should be, derivative of the square root function is 1/2 times the inside function raised to minus 1/2 times the derivative of the inside function, which is 6, right? That's that. On the denominator, derivative of y, 1. Now substitute the 0 there, and that will be it. So this will become 1/2 1 plus 6 times 0 raised to minus 1/2 times 6, all divided by 1. Compute this. This should be your answer, right? Look, this is 0, disappears. 1 raised to any power is just 1. I am left with 1/2. 1/2 times 6 is 3. 3 divided by 1, just 3, right? 3. So final answer, 3 here, 3. This guy for number 8. To finish, let me do this one, which is short, very quick, just in case you need help on your homework. This way we did, probably this, right? 12. What to do if they give you something like this? 2x times cosecant of x. Cosecant of x. I'm going to do this one. Probably, if this time I can ask you to do 13. Okay. Rewrite this as 2x times 1 over sine, because recall cosecant in trigonometry equal 1 over sine, right? Comes from trigonometry identities. 2 times x times 1 is 2x over sine. Looks better now, right? So This is something that you can deal with, right? Because if you substitute 0 and 0 here, you get 0 over 0, right? Which is the green light for L'Hopital's rule, right? L'Hopital's rule. This means that we can apply L'Hopital's rule. So taking the derivative of this guy, derivative is just 2, derivative of sine, cosine of x, and you have to take the limit of this as x approaches 0 from the right. At this point, just substitute 0 here. We get 2 over cosine of 0. Cosine of 0 is 1, right? So 2 over 1, just 2. Follow, guys? Yes. Right? Just 2. So maybe you can try this one on your own, and then so to finish this up. Limit as x approaches 0 from the right of 10x. Hint, right? Rewrite this as 1 over sine of x, right? Yeah. And then continue there. Okay, let's do it together, right? This should be equal to the limit. 10x times 1 is just 10x. Sine of x on the bottom. Aha, I see some answers here. Gonja, excellent, excellent, right? Yeah, very good, excellent, you got it. Very good. So then we know that if we attempt direct evaluation, this will be 10 times 0 divided by sine of 0. I get 0 over 0, right? Which is the green light for me to go ahead and use L'Hopital's rule, using L'Hopital's rule. L'Hopital rule says take the derivative of this guy, and trade this quotient by the quotient of the respective derivatives, right? Derivative of 10x is 10. Derivative of sine is cosine of x. Once you do that, try again the direct evaluation, and you will see that now it should work. 10 divided by cosine of 0. Cosine of 0 is just 1. 1 into 10, just 10, right? Very good, guys. Try to remember this for your homework.